Again, a warm welcome to everyone joining for today's webinar of this EC series on risk in space weather, in space. And today we have with us someone who has been working on these topics for many years, Norbert Jakowski. He's now retired from the DLR, but he's been working. He graduated from the University of Rostock and then very soon joined DLR, where he's been working, spent his whole career on the ionosphere, radio wave transmission through the ionosphere with all its applications. And he's still working on that. So whenever someone's mentioning GNSS and space weather in Europe, very quickly his name comes up, also because he's been involved in many projects. So welcome today with us, Norbert. Before we start, just a few indications. As usual, if you have questions, please don't hesitate to write them down in the chat. After the presentation, we will have time to go through them, and I'll ask you to unmute your mic and so that you can ask your question directly. So if you have questions, please keep them for after the presentation. You're welcome to do so. And with that, I think we're ready to start. So the floor is yours, Norbert.
Thank you, Terry. And also, I would like to thank ISI for organizing this nice online meetings. It's very, very exciting. And welcome everybody to my talk dealing with space weather impact on radio wave propagation. After a short introduction, I will clarify some important terms, ionosphere and fundamental of radio wave propagation. And then I would like to show and discuss some impact scenarios for telecommunication, space-based navigation, and remote sensing. Radio waves play a significant role in our modern society. Everybody knows that we, in our smartphones, so we have these core business activities, telecommunication and navigation, and these have a big practical meaning in our society. And insofar, it's very important to know what are the vulnerabilities of these techniques, eventually not only to man-made noise or attacks, but also due to space weather. This is our topic today. Especially for navigation, we know that the satellites, the GNSS satellites, orbit the Earth in a distance of 20,000 kilometers, and they cross over the geoplasma, that means the plasma sphere, ionosphere. And because these are electromagnetic waves, they, of course, interact with these charged particles of ionosphere and plasma sphere. And therefore, we expect some interaction. And this is a topic of my talk today, to discuss these things in more detail. Let's have a look back to the history. James Clerk Maxwell, based on the knowledge at that time, formulated the theory of electromagnetism. We know the famous Maxwell equations. Later on, Heinrich Rudolf Hertz approved this theory and could show that electromagnetic waves, radio waves we call it nowadays, can be created and are similar to light, as we know. Guglielmo Marconi made a lot of exercises to transmit radio waves in the first time at shorter distances, but then he had a fantastic idea to apply this technique he developed together with others also at that time to overcome the distance between England and American sector. He thought that the wave can follow the sphere of the curvature of the Earth's surface, but according to Rudolf Hertz, Heinrich Rudolf Hertz, it was assumed that light travels along a straight line. So this was a fantastic idea, but nevertheless, he gave not up, and then he installed a spark transmitter. This was a radio transmitter at that time, created a big antenna system and also at this receiving side to have enough power to overcome this distance. And it worked. So in 1901, it is said that he could transmit the letter S, that means 3 dots. And to explain this, there were some people, 2 people, Oliver Heaviside and Ernest Kennelly, who made the assumption that there must be an electrically conductive layer in the atmosphere that causes a reflection, then we can overcome the distance. By the way, Marconi got a free ticket for the Titanic maiden trip, and because this ship had a Marconi radio station on board, and though there was a possibility for him to go with this Titanic trip, but he was very busy and could not. He used another ship 3 days earlier, but nevertheless, his radio device contributed a lot to the life of about more than 700 people who could be saved during this disaster due to the radio transmission to the emergency calls this Marconi system sent around. And other ships came and helped and could save the people. And in the same year, there was an international radio telegraph convention meeting where they decided to standardize and make some international rules for such emergency calls, because in case of of this Marconi radio system, this was not free for everybody. It was only related to the Marconi stations. And the Marconi company gave up this policy, and then they came to international regulations to make the shipping over the oceans more safe. This was a very important issue. In next years, there was developed by Appleton especially a theory of radio wave propagation and plasma, and he got the Nobel Prize in 1947 for this fundamental work. So this is a very important issue, and we can say that since Marconi's successful experiment, there's a close relationship between radio wave propagation and ionosphere. This is up to date, I would say, and a very important point. When talking about radio wave propagation, we have mostly also include the ionosphere. And the ionosphere is also a point or a component of space weather. We know the sun is a motor of space weather, or the mother of space weather. And this emits a lot of radiation in the broad spectrum of electromagnetic waves, from X-rays to infrared and even to radio frequencies. And also the sun emits some particles which can also ionize the atmosphere. And so we have different layers, and they are coupled together and so on. And so far, the ionosphere is also a part of the space weather impacted by the sun. Let's have an illustration of this. We have the solar radiation, we have the electromagnetic waves, ionizing electrons and ions, ionizing the atom and molecules, produce an electron and ions, the same as with energetic particles. So we have an ionization profile, a vertical electron density profile here in this case. And at daytime, we have ionization, it builds up, and in the night there we have the recombination, and then the ionization goes down. So have it every day. These up and downs have a high dynamic variation of the electron density. What happens if we have a radio wave in the plasma? So we have the ions. These are have a big inert mass, more than 2,000 times than the electrons, and they can follow lower frequencies, whereas the electrons can follow higher frequencies. So if they follow fully these waves, then we talk about resonance. So for ions, this is in the kilohertz range, and for this electrons, this is a megahertz range. And this interaction has some impact on the radio waves, of course. It changes amplitude, phase, polarization. We will discuss these issues later on in more detail. And the correlating or associated processes are absorption, refraction, diffraction, scattering. So these effects play a role and should be considered. At first, let's have a look on the refractive index, because the waves are not propagating in the vacuum as written here by Maxwell. We have to take into account this plasma, and Appleton developed a theory together with Hartree and Lassen, for instance. So they have developed some expressions for the refractive index, which is written here in a complex form. And these terms have some relation to the plasma frequency I mentioned already, and the gyro frequency and the collision frequency of particles like ions and electrons with the environment. And you see this set here in this complex way. And this is a contribution to the absorption. If the collision frequency is in the order of a kilohertz range, then the probability to have some collisions with neutrals also is high, and we have a loss of energy. This is extracted from the wave. The other thing is this gyro frequency. So we have if you have a magnetic field, because we call magnetized plasma, the ionosphere is embedded in the geomagnetic field. So we have rotation, a gyration of the electrons around this magnetic field, and we call it gyro motion. And you can imagine that if you have a polarized wave, which is in this has a polarization in this direction as this, for instance, for the electrons, then the refractive index is different if you have a polarization opposite to this. And insofar, we have double refraction here, which has to be considered. For instance, the GPS polarization is right-hand polarized. It fits with this picture here. But if we have the ray path of GPS in this direction, it is opposite. So the gyration direction of the electrons, and then the result is another refractive index, and this causes asymmetry. We will discuss this later. At high frequencies, we see that this absorption can be neglected because this collision frequency is in the order of kilohertz, and here we have gigahertz in case of GPS, for instance. So we can, in the further discussion, we can consider if F is bigger than FP and the collision, then we can develop the refractive index in this way. We have different terms here. This is the first order term with the plasma frequency I mentioned already, but now we see that here in this term, we see the electron density explicitly, which contributes to this first order term. In GPS, for instance, GNSS, we have at L1 frequency a contribution of less than 100 meter normally. Then we have the second order term I mentioned. This is a double refraction depending on the direction of ray passes, how they go through the geomagnetic field. We have different angles, and insofar we have different effects here, asymmetric effects. We will see it later also. The effect is in the centimeter range, and we have a third order effect. This is millimeter range. The phase velocity of this wave is can be considered by this ratio C over n, and in this case we see the n is less than 1. That means the phase velocity is bigger than the velocity of light. This is a very important point we will discuss later. So here's an overview of the different radio waves. We can distinguish different frequencies, accordingly the different wavelengths, and they behave in a different way. Whereas the lower frequencies are reflected at the Earth, at the ionosphere in the lower part, the HF, if this is if the frequency is equal to the plasma frequency, it is reflected. And if the frequency is higher, at in the VH, very high frequency case, the wave can travel through the ionosphere. And there has a special ray path shown here. We'll discuss this also later. To estimate the impact on the radio wave propagation, then we have to learn a little bit about the ionosphere. So there are different methods possible: vertical sounding, in-current scatter radar, also GNSS can contribute with the integral of this, and radio occultation measurements can also provide the profile of the electron density. So we have good options to get some information about the electron density profile. And this is due to the fact that the ionosphere, the plasma, changes amplitude phase, has a certain delay in polarization, and measuring these deviations, then we can get some information about the ionosphere. On the other hand, knowledge of the ionosphere gives us the possibility to understand, to predict propagation of radio waves. Insofar, such investigations are very important. Here I will illustrate a little bit how the terrestrial radio wave propagation works. So we have a transmitter, we have some receivers here at the ground, we have the ground wave. So all frequencies can be used for this ground wave, but for the sky wave, that means this requires a reflection at the ionosphere. There are some limitations, and so we have here some ranges of frequencies which can work. And in this case, for instance, so we have some interference between ground wave and sky wave, so it gives some problems eventually. And if we have farther distances, so we have only this sky wave available here, and like Marconi's experiment, so we can have a far distance communication. But if we have a proton event or a flare, then a part of the energy of the incoming waves is absorbed. And this means that the field strength is reduced at the receiver side. It may cause problems, but it causes indeed problems if you have a serious proton event or very strong flare, then you have no signal at the user side. This happened, by the way, when Ronald Reagan tried to go to China one time, and this was in April '84. There was a strong solar flare effect, and the airplane, Air Force Number 1, had no information, no communication with the ground stations. This was a crucial situation for them. So in this case, we talk about a blackout effect or short wave fade out polar cup absorption effect. And this is well represented in the NOAA space weather scales. You see here the X-ray values, the levels, different levels, and the different effects on HF communication. The same is for the S scale, the NOAA S scale, solar radiation scale. There are indicated here the solar protons. Both these effects can cause this problems in ionosphere propagation. And here's another point I would like to draw your attention on this, because we have at daytime, we have, due to the higher energy components of the solar radiation, we have the a D layer existent, and this D layer absorbs also some radiation, and this is a daily, happens daily, and limits the frequency that can be used for communication, for instance. If you know still these old receivers, then it was interesting to know at daytime you could also observe only listen to ground wave receivers in the neighborhood, and in the evening hours when this D layer disappeared, then you have a blank mirror here, and you could receive radio transmitters from Africa and Europe here, and from very long distances. And in that case, also we have some interference of different transmitters. Here's another application. This is over the high horizon radar. For instance, in Paris, near Paris, we have such a radar working with a reflection at the ionosphere. It can detect bigger ships or even airplanes. This was created for military purposes, and of course it is sensitive to the ionosphere. If there are some perturbations, then one should avoid misinterpretation of these results. Another effect is it can be detected by VLF. I mentioned it already a little bit. Here we see the GOES solar flare registration in the X-ray range, and here we have a strong variation of the field strengths here indicated simultaneously with this X-ray, because we have a strong absorption in the lower ionosphere, and then you can detect these. And in DLR we establish such a system, global ionosphere flare detection system around the world, to have all the links, at least in the sunshine, to have around 24 hours such information to measure the flares. I would like to draw your attention also to this very interesting experiment. We have all the students project in DLR Neustrelitz, and this uses also VHF, the VLF measurements. And what we have detected here is a gamma ray burst. You can see it here, and it is a very rare event, but it is very interesting to see that we could detect it here, and students are very proud of this. And of course, this project is also open for international contributors. If somebody is interested, can contact us to join this project. Here you see the corresponding X-ray measurement from the orbit, from the satellite. And this can even measured by changing the ionosphere propagation conditions. And let's summarize these ground-based effects. So we have we said that our radio waves at frequencies below 10 megahertz are mostly reflected by the ionosphere. We can have long-distance propagation, sometimes several hoppings here, or reflection on the Earth. And again, ionosphere, you can go around the Earth. And there are some services providing information about the maximum and lowest usable frequency for communication. And sometimes we have seen solar flares and particle precipitation can lead to a blackout effects. And these things have to be taken into account in HF communication, for instance, for polar routes from United States to Asia sectors, other cities. They use these polar routes because this is a save of time and money. And on the other side, they have other disadvantages with particle precipitation, in the aurora zone especially. And we have just mentioned that we can have fading and blackout effects. And insofar, there is a service provided by the Space Weather Prediction Center in Boulder for these things to make these flights more safe. And I mentioned already the event with Ronald Reagan, who lost the communication. Let's go now through the trans-ionospheric propagation of radio waves. This is a point we are interested in GNSS studies, and you know GNSS is applied everywhere in many fields, and we cannot imagine a world without GNSS at the moment even. And insofar, this is of very big interest for us to have a more detailed view on the propagation. And we see here the following. We see here the ray path of GNSS. This follows the principle of Fermat's of the fastest arrival. And we have seen that the refractive index is less than 1. That means the phase velocity is in the ionosphere is bigger than the velocity of light. That means that the rays travel very fast in the ionosphere. This means this is the reason for this curvature. The rays like to stay in the ionosphere as long as possible, although the travel time must be a minimum. But this time is lower than if it would the ray would go this way. And this is a very interesting point. And insofar, one has also to consider this ray path extension in practical application. There's not much, as we will see later, but this curvature has to be taken into account also. And we see here, if the frequency is higher, F1, this effect becomes smaller and smaller because the electrons cannot follow these waves if the frequency is increasing. So here we have the observation equations for the GNSS measurements. So we have here the distance we would like to determine. We have the time, and what I would like to focus on is this ionospheric error. Here, in this case, we consider the first order effect. As I mentioned already, this is related to the S-tag, and this is a carrier phase. This we discussed here. In this way, this is a negative sign. This contributes to the phase advance, as I mentioned. But for the code measurements, we have a plus sign here. This means that the signal propagation velocity is bigger than the velocity, is smaller than the velocity of light. So this one has to take into account. This is a difference. And if you calculate code phase differences, then you get an expression to derive the slant TC. This is, if you have this, you can also make the correction. And insofar, this is an important issue, but also, of course, for ionospheric studies. So the trick to do it in good quality is the following. You have an absolute value by using the code measurements, and the relative values by using the carrier phases, but they have some ambiguity with you don't know how many wavelengths you have to take into account. And insofar, we can use this code phase measurement, but they have a big noise because the modulation is with 1 megahertz and 10 megahertz. So we have big noise here, and this would be not so good to have a good quality of TC estimates. The procedure is so that we level the this carrier phase difference into this absolute measured code phases, and then we switch over to the carrier phase differences, and then we can calculate the S-tag in good quality. This is a procedure, and in DLR we have the following procedure to produce TC maps. So we have these measurements, and we compare the data with a model, and then at each grid point, and then we get some results, as we can see here. The advantage of this technique to use a background model is that we can have the data over the oceans where we have no measuring points. Here you see the measuring points, the ionospheric piercing points where you get the information for this. Here's a simple example how it works, the positioning. So we have a 2D presentation. If in vacuum we have a very accurate crossing of these circles according to this to the velocity of light and the time measurement. But if you have switch on the ionosphere, then the time is delayed, and it means that you have interpret this as a longer distance. The same here, and that means so we have a failure, an error in the positioning. You can overcome this by using some monitoring over a certain region. You here, for instance, assuming that we have a car here in southern Italy, then you take this value, you get it here, and then you insert it here, and then you can correct the position for this navigation. This is one option, and it justifies some services in this way to provide users with such an information. Another possibility is to use a model to make a first order correction. So GPS uses the so-called Klobuchar model. This is a very simple model here that is able to correct the ionosphere error up to 60% about. For Galileo, we have the so-called anequic model, which is a 3D model, which doesn't need the mapping function to convert slant into vertical and vice versa, but has to calculate or integrate the electron density along the ray path. This is a time-consuming process. The Chinese system has also a model involved, which is updated permanently. And I'm really happy to see that also our model, our Neustrel's TC model, is considered by the European GNSS Service Center as a Galileo alternative model. This has only 12 coefficients. And solar activity control parameter, this is in the original model, the F10.7 index, is used here or reconstructed from the AZ parameter here, which is used in anequic model in Galileo system to refer to the actual solar activity conditions. And it works quite nice, so we get the same similar accuracy with as anequic, or through anequic. We have only 12 coefficients, and anequic has more than a few thousand coefficients. Therefore, it needs some more time for computing. Yeah, here's some examples of the higher order reflection effects. As I mentioned, here we have some sample here for the Faraday rotation effect, the second order effect. And you see here the asymmetry, because in one case the ray path is with, and in another case against the magnetic field, and you see the asymmetry here. These are 20 millimeter. This is not much, but you see the asymmetry here. And this second order reflection error is at the moment already included in orbit calculations, satellite orbit calculations, and so far plays also a role in the practice. For radio occultation measurements, you see the ray path again, like the ionosphere, goes this way to the maximum of the peak density, and also has to be taken into account when you calculate the electron density or from the radio occultation data. There's an option to mitigate the ionosphere effects in a certain way, the so-called ionosphere linear combination at two different frequencies. You can compare the phases at two different frequencies, and then you get this expression, assuming that the other errors compensate more or less, and then you have this expression. but because this is a nonlinear relationship with the frequency, the dispersion is nonlinear, and therefore we have a rest error, which cannot be compensated by such a linear combination. And here we have a figure where we can see the rest errors, and also included is here the ray tracing, the extension of the ray path, because it deviates from the straight line. So this is below 5 centimeter here for carrier phase measurements, and for the group, for the code measurements, this is 15 centimeters, so it's not so much, but in very accurate applications, this has to be taken into account. So that means dual frequency receiver, dual frequency measurements depend more on ionospheric perturbations than on the regular ionosphere. This can be modeled nicely and corrected. So what kind of perturbations we have? We have small and large scale, and in between. So all these differ by different scales in time and space. And the question is how we can characterize these different situations in the ionosphere, though in analogy to indices used in geomagnetic and solar physics. So we think that we can use also some indices which characterize the average behavior of the ionosphere in a statistical sense. So we have some applications here, for instance, a differential network, a German company. We have the tech rate here. We see during a storm, this perturbation is moving from higher to lower latitudes. And in the same way, we see a degradation of the accuracy achievable by this company from north to south. It shifts with time and reduces finally, because here we have here not such a strong perturbation. The same is similar thing for the well-known Halloween storm. So we see here the availability of the satellites and the solved situation. In this case, at the time, there was no solution possible, and this is due to the effect that that in the ionosphere we have a lot of perturbations here. And for instance, so we have a tongue of ionization from the day side to the night side, and other processes which contribute to strong perturbations in the ionosphere, influencing the phase and amplitude of the rays. And here we have seen some particle impact. Here's the same storm in a different picture. Here we see the DST variation, and here in the course of the storm, different behavior. We see in the onset time, we see some deviation, positive deviation of the ionization, independent from the latitude. This is probably due to the convection electric field, and later on we have some processes related to some transport processes, excuse me. And we see also the tongue of ionization, also registered here via CHAMP. So all these things are quite nice. We see also the moving of the trough region with patchy structure in the high latitudes. At that storm, we have seen polar lights indicated here by this trough region in the lower latitudes, even in southern part of Italy. How to overcome these problems in aviation, for instance. Aviation industry is interested to use also the GNSS system, of course. And so they have established several systems, so-called space-based augmentation systems. The functionality is given in this picture. Here we have GPS or Galileo satellites or whatever. So here we get the information about the ionosphere and the stations ranging in integrity monitoring station. This information is then provided to the center, and we get the information from different places over Europe. And then this information is provided to a geostationary satellite, and this satellite provides all the users here with correct ionospheric error information. Why this is needed? The problem is that airplanes have only a single frequency receiver. This is a problem, because therefore they need this first order correction at least. And so far, such a service is needed. Now, this is a problem and has to be overcome by space-based augmentation system and ground-based augmentation system. I will show later. Here we see the impact on these systems also if we have strong deviations, strong storms in the ionosphere. Here we see as a parameter the TC, a deviation from the average over 27 days, one solar rotation period. And we see that the functionality of EGNOS is reduced, seriously reduced. This is an area where it works, but other areas doesn't working well. And the same is with wars. We see here the TC 1 day earlier, here a strong TC enhancement and also a failure in the war system. So it could not work fully operational. Though we see there is a strong impact of the performance due to space weather effects to ionospheric storms. To overcome these problems also in a certain way, ICAO, the International Civil Aviation Organization, is just building up together with consortia in Europe and in other regions of the world, some space weather centers around the world to get some information on the state of the ionosphere. For HF communication, as I have reported, flares and particle precipitation. For GNSS navigation, and additionally also the radiation exposition at flights is important for passengers. Here's another system also for aviation. This is a ground-based augmentation system. This works a little bit different. So we have the information about the ionosphere and the airport area by some ground stations. Here is indicated here. And then you can have, then you provide your measurements to an airplane approaching. And in this case, for instance, the airplane looks to another ionosphere, much more higher ionized. And though this system would provide wrong information to the plane, is so-called hazardous misleading information. And this is, of course, dangerous. And so far, one needs some information about this. And we have, for instance, developed some gradient index, which measures such gradients to provide user with this information. Of course, this is a quite interesting thing. And we see here some motion of such a gradient index. The northward gradient index is here, and how it propagates during the storm over Europe. Here, this is the period we consider for this St. Patrick's Day storm. And we have this here in high latitudes. We have some irregular behavior. If we come to lower latitudes, to mid latitudes here, we have a well shaped gradient structure we will see here later on, and it disappears when we go down to lower latitudes. And you see here the well seen region of this gradients, and here positive gradient, here negative gradients, and this can help to support users. And also we can make some forecasts if we derive some information on the velocity and the direction of such ionization fronts, we can help users in this case. Another problem is temporal variation. If this is very rapidly, you can lose a lot of information. The receiver cannot follow this. Here we have the flare before the Halloween storm, and we have developed a special index SIDX we call, which takes the temporal variation of all piercing points and adds these and averages it, and then we get such a result here, very sharp, and it correlates very nicely with positioning, and so we believe that this information can also help to this measurements. The same is with other indices, for instance, with a well-established rate of tech index, so ROTI, and here we can see the flare also all over Europe, because it's not only a single place that is large-scale effect flare, of course, in the sunlit ionosphere. We can see it, and this is another point. So that means one has to discuss a little bit the different indices, the different types. They give different information. At the moment, the NOAA space weather scales doesn't address trans-ionospheric radio wave propagation. I have shown this R scale, for instance, and there's a need to have another scale additionally, and we have some activities via the International Space Weather Action Team to address this topic in a special team. And if you're interested in this topic, please contact me and you can join this via this address. We have regular meetings to discuss these issues because we believe it's very important to have this trans-ionospheric radio wave propagation index on the scale for this to support trans-ionospheric users. So I have to address also a little bit the diffraction effects, the small scale effects. So we have the very small turbulences, small scale turbulences in the ionosphere. So we see that we have a superposition of different rays here, resulting in this big perturbation, positive and negative, and it may lead to a loss of log here. In this case, the indices IS4 and sigma 5 for these small scale error scintillations, and these play a certain role when we measure it. What happens in case of loss of log? So we have a strong variation of the signal strength, and in some cases there's a very strong fade, and this can lead to a loss of log. Smaller effects make enhanced noise level, cycle slips, and so on. And so far, one has to take into account this. We know that the different systems have different effects, so this has to be also discussed in the future work. Of course, we have to know the physics of these small-scale irregularities by theoretical studies, by measurements, the diurnal variation, and all these things, direction, and so on. And so one can make some contribution to have a forecast in the future or a better nowcast to mitigate such problems in practical application. And a point could be also to insert measurements into a model, as we have done it for, or have shown it with for TEC. So we can reduce the inaccuracy of the model in a certain way, but this depends on the number of stations. If we are, and the scintillation receiver are costly and rather rare. So insofar, this is a problem to have this picture applicable. But in recent times, though, there have several papers show that there's a strong correlation between S4 and ROTI and low latitude especially. And then due to this high correlation, you can use ROTI measurements as a measure for scintillation activity, and then you can contribute to the mitigation of such effects. Let me come to remote sensing only with one slide here. We have the same problem as for navigation. This is a ranging problem, and we can see sometimes some ionospheric structures here due to ionospheric perturbations, in addition to ranging, which follows this term of TC. We have also the polarization, because biomass explorer, for instance, uses P-band, and then we have strong effects due to the lower frequency, and the polarization plays also a role. We have the Faraday rotation effect depending on the density and the magnetic field orientation. All these things depend on the ionosphere, has to be taken into account. And a new technique, GNSS reflectometry, this is also applicable, and I will not talk about this, but this is another option. Another option, nothing to do with it, has nothing to do with the ionosphere, but with space weather in general. There can be a strong impact of solar radiation on GPS signals, because we have radio frequency range of in the solar spectrum can have very high values, and these high values can via interference reduce the signal strength, which we can use for positioning. And insofar, there's also a danger, considering that the power of GPS or other systems is very low, only in the a few watts, so to say, like a lamp, though, and the distance is very strong. So one has to. There's a certain probability that during very strong events, radio bursts, we have some interferences happened in Sweden. Klaus Sievert has talked about this. There was the airport in Stockholm, Malmö was down, was closed for a certain time. And so this may happen. For all the GNSS applications, it's clear that also man-made noise can also disturb such signals because they are so weak. For SATCOM application, satellite communication, we have also some problems in case the satellite, the antenna look into the sun, so to say, directly into the sun, then the probability is high that you have also some interference problems. Yeah, let's come to the end. So we can say that radio signals used in HF communication, space-based navigation, and radar systems are impacted by ionospheric plasma due to refraction, absorption, diffraction, scattering. The ionospheric delay is the largest error source for single frequency GNSS, and also a significant factor for differential GNSS. Ionospheric storms and small-scale irregularities may cause performance degradation in precise and safety of life GNSS application, and also, as I've shown, in remote sensing system. So the conclusion is that monitoring, modeling, and forecasting of ionospheric behavior and derived near real-time products like proper indices will further support mitigating ionospheric impact on radio signals as used in telecommunication, space-based navigation, and remote sensing. So that means there's enough to do for the future, and I would like to thank you for your attention.
Thank you so much, Norbert, for this wonderful panorama of everything that's happening between us and the ionosphere and all the consequences. Okay, so now we have a time for questions. So in the audience, if people have questions, please don't hesitate to write them down in the chat, and I'll go through them as they pop up on my screen. So there was a first quick one by Casper van Dam. He's asking for the Air Force One event, when Ronald Reagan was flying to China. Do you have a reference for that?
Yes, I have a reference, but I don't know immediately, but I can send it. You can send me an email, I will send it.
Okay, I hope you got it. We move on to a question by Jim Klimchuk. Hi, Jim. I'll ask you to unmute your mic so you can ask your question directly. That would be easier. So let me just...
Good, can you hear me?
Yes, it's not so loud, but it's okay.
All right, well, thanks very much for the very interesting talk. I'm especially interested in effects associated with variability of the solar radiation on timescales of 1 to several days. So the kind of variability that's connected with the evolution of solar active regions, or the rotation onto the disk of active regions from the backside, or the rotation off the front side to the backside. And I've been told by some folks in the military, they're kind of reluctant to provide too much information, but they seem to be especially interested in scintillation. It's a big problem for them. And I understand that the level of scintillation is dependent on the background level of solar EUV radiation, a slowly varying component. Can you please say more about that?
Yes, the background plays, of course, a big role. If you have a high ionization level, then the intensity of scintillation is also stronger, because this is also, for instance, the background ionosphere is also included in scintillation models like GISM. And this is a very simple connection then. If you have basic ionization high, then the variations are also high. So this is a very important point. But for high and low latitudes, there's a physical difference. So in high latitudes, you have more refractivity and not so strong amplitude fluctuations. So this is a different physics. This needs some further investigation. So this is an interesting topic nowadays.
Okay. If you would please provide a reference or references on these aspects, I'd be really appreciative.
Yeah, of course. Yeah, I can send it to you. I need you know my email address. Please send me an email. I will answer.
Great. Thank you so much.
Perfect. Okay. So we have another questions by Nayaki Nita. I let you unmute your mic and ask the question.
Can you hear me?
Yes.
Yeah.
Yeah, thank you very much for this very informative talk. But I wonder if out of the 3 NOAA space weather scales, geomagnetic storm flare and energetic particles, the effect of energetic particles seems to be quite elusive to me. I don't really understand how protons coming from the polar region can affect something global, ionosphere. Is there any reference about those things?
I don't understand your question. The proton events are focused on high latitudes.
High latitude, yes.
Yeah.
But are there any very severe effects compared with temporary flares or geomagnetic storms that come later? The part of the contribution from solar energetic particles, are there examples of events that show energetic particles cause the GNSS disturbances more significantly than flares or geomagnetic storms?
You mean you would like to have a reference where proton events disturb GNSS?
Yes.
Yeah. Okay. Yeah, the proton events are mostly focused on the lower altitudes, as I've reported. And
Okay.
insofar, the perturbation for GNSS is not so strong. This is more related to the HF communication, as I have pointed out. And for flares, there's a difference because the flares can be composed on X-rays and EUV. And X-rays, they work or act in the lower ionosphere and have no big impact on GNSS. But the EUV component, if this is strong, you have an effect in GNSS, as I have shown in my sample.
Okay.
So we have to distinguish between the spectrum of a flare, and this can vary from flare to flare.
Okay, thank you very much.
Welcome.
Okay, so I have a question. We have a question by Simona de Palma, but I don't see her on the list anymore. Let's see. No, unfortunately. Okay, so let me still ask a question. It was a quick one. It's about how you use the tech gradients in order to increase the GNSS performance
how I use tech gradients?
Yes.
Yeah, okay. Yeah, it's
That's
the
all I
beginning.
have, unfortunately. She's not online anymore.
Yeah. I have shown one example where it becomes clear that gradients are very important, because if you have a user and the measurements and they have different ionization level, there's a gradient in between, you have some errors if you would like to how to say, inform the user with your information. And we have developed a special index, GIX, as I mentioned, gradient ionosphere index, and this exactly is able to monitor the gradients. And we are at the beginning of this development.
Okay.
And so far we look now for some application. So with surveying companies or with in aviation for ESSP, for instance. So we hope that we can contribute with some information which is valuable for them.
Okay, that's interesting. So we have a question by Sadia. If you can speak up. You're still muted. Okay.
Yeah, Prof, thank you for your informative presentation. So I would like to ask you a question that what is the actual impact on equatorial regions of the geomagnetic storms? And what parameters like the KP index or the A or AP, what parameters need to be focused to precise the DIX model or disturbance index?
Yeah, okay. We have to distinguish a little bit the storm behavior in the ionosphere, which propagates from high latitudes mostly towards lower latitudes, and the scintillation behavior. The most important issue for GNSS perturbation in the future will be these small scale irregularities, because all systems are impacted, so to say. And it is so that this scintillation is caused by some effects in the atmosphere, because the dynamo effects in the atmosphere creating some electric fields and causing some electromagnetic drifts of the plasma, and in such a way the scintillations are caused. Whereas the ionospheric storms propagating from high to lower latitudes, they have other characteristics. They have TEC enhancement, for instance, all with some gradients, but they can create the opposite. They can destroy the regular mechanisms which we have practically every day due to lower atmosphere processes, can destroy it even. So in some cases, the scintillation is not so strong as usual during storms. Insofar, this is a very complicated manner to distinguish between the different effects. And this needs further investigation, of course, to better know how scintillations are created, and by modeling studies, in particular, also to compare it with measurements, and also the propagation of storms coming from high latitudes to lower latitudes.
Okay, thank you, Prof.
Thank you.
Okay, and the next question is by Antonella Nota. So Antonella, if you want to speak, yes.
Thank you, Norbert. This was fascinating, really fascinating. So speaking as a non-expert, totally not expert, just a curious astrophysicist for this kind of phenomena. So what's your feeling? I was reading recently about the Carrington event from the mid-1850. Yeah. What's the probability that we experience such an event in our lifetime? And which one of your, the method that you outlined, can we do anything to predict it or mitigate the impact?
No. This has to be answered by solar physicists also. What we can do is the following. In Neustrelitz in DLR, we received the DISCOVER satellite. So we have an early information about the space weather condition, or the space weather, the solar wind. And then we can make a prediction when this coupled into the magnetosphere, ionosphere system. And then we can measure at the ionosphere, as I have shown this movie of the gradient structures. Then we can derive the velocity, propagation velocity, direction. Then we can make some prediction for users, for GNSS users, for instance, or others. This is our way to handle such a problem. To predict solar events, solar disruption. So this is beyond our scope, of course. So and even, I believe those solar physicists have also some problems to solve.
Yes.
We wish we could do it, but thank you.
Thank you. Thank you.
Actually, for those who are interested by this issue, there was a talk given on this topic precisely by Ilya Ozoskin that was back in November last year. And indeed, he said he couldn't make any predictions statistically yet, but yes, but not. So we have a question by Rob Robinette. Okay, let me just find your. Can you talk?
Oh, hello. I'm just wondering if the measurements of high frequencies in the 3 to 30 megahertz range for propagation measurements could make any contribution to validation or prediction of the trans ionospheric models that seems to be the major area of interest for you.
You mean trends, long-term trends in the ionosphere, yes?
Or even short-term. I'm heavily involved in the WHISPER weak signal propagation recording, and I'm wondering if we've recently made additions and refinements to the measurements that are being made there, which have given us some insight into high frequency propagation, which is of course due to the refractive transmission and I'm wondering if there's any possibility that these measurements might be useful outside of our amateur radio, transmission.
I believe every measurement is of certain interest. The question is how convenient we can use them. This is a point always. But if you have more knowledge, you can have a more can give comprehensive answers to some processes in the ionosphere. We are far away from knowing everything, and insofar any information will help. So I can
let me see. I can send you a link to our website and our database, and it would interest me if you see any value in your studies.
Okay, let's discuss this in more detail. Okay, thank you.
Very good, nice. Thank you for your presentation. I learned a lot.
Thank you.
It's really loud.
So we're getting close to the end. I still had a quick question. Sorry, I had actually several questions, but let me just keep one. So in recent talks, we heard about long-term trends in the ionosphere with cooling and gradual lowering of the altitude. I mean, on timescales of decades. Has this any measurable impact already, or is this just beyond reach for your measurements?
A measurable impact, I would not say, but we use, of course, the TEC measurements and ionizing measurements to derive something. So we have made a publication on this subject. For instance, if you measure TEC and NMF2. TEC over NMF2 gives the so-called slab thickness. That means the width of the profile, of the vertical electron density profile. And what we found is the width of the profile is decreasing over the last 2 decades. So this we have already published, and we are just preparing a new publication, on this topic with an extended database to see what happens. And the effect of the slab thickness was dramatically, I would say.
Really? Okay.
Was very strong. And this method has the advantage that you can eliminate the strong solar activity impact on NMF2, on the peak density, and on TEC. We have a strong variation. But if you have the ratio, then the slab thickness is not so impacted by this, by the solar activity. And furthermore, it is related to the neutral gas. because according to the Chapman theory, this slab thickness is related to the neutral gas scale height under equilibrium conditions, of course, only. And though you can have some information on this cooling, and we see a really dramatically lowering of the width of this profile. It has no big meaning on GNSS because it reduces in principle the TEC, I would say, and it has no perturbation meaning. This is a long-term trend, a more regular effect, and but it's of physical point of view very interesting, of course.
Yes. Yeah. Okay. Well, thank you for that. I think this brings us to an end. I would like to thank you again. Very warm thanks for your presentation. Very comprehensive and clear.
Thank you. Thank you.
And there were many acknowledgements and thanks in the chat, which you will get shortly. And just to the audience, to the attendees, I just would like to mention that we have 3 more talks planned in this series. The next one will be about using artificial intelligence for predicting or mitigating space risks. Let's see what this gives. This is next week by Enrico Camporeale. And after that, there will be a break and we will start a new series, but on a different scheme in the sense that it will be a monthly webinar, I should say. And we will be addressing different topics in astrophysics, planetary sciences, heliospheric sciences, and so on. So please stay tuned on these EC webinars. So 3 more to go in this series, and then there will be a short break, and then we move on with a new series to come with more surprises. So thank you again very much, Norbert. Thank you all for listening.
Thank you also. Thank you also for inviting me and for this nice opportunity to have it here in EC. Thank you.
Thank you very much. Goodbye.